Hello again, AP students. In today's lesson, we are going to look at vector multiplication. And as I mentioned in the previous lesson, there's actually a couple different ways that we can multiply vectors together. There's one type of vector multiplication that's referred to as a dot product, which is significantly easier to deal with. And another form of vector multiplication referred to as a cross product, which is probably one of the most tedious things you will ever do in math. Okay, so let's just jump right into it, considering how anything that's tedious takes a lot of time to go through. Right, so let's start off with something called a vector dot product. A vector dot product involves taking two vectors, multiply them together, and that gives you a scalar quantity. Now, it turns out that we've actually done this back in Physics 20 when looking at calculating work. When we calculated work involves the multiplication of force, which is a vector, by displacement, which is a vector. But then oddly enough, a vector times a vector gave a scalar quantity, which seems a little bit not intuitive because you'd expect a vector times a vector would give you another vector. But in this situation, a vector times a vector gives you a scalar. And again, a scalar does not have direction to it. Okay, so let's word this in terms of like more generic mathematical variables and as ordered triplets. So we have vector A, which has components ax, ay, az, and we have vector B, which has components bx, by, and bz. And what I want to do is I want to multiply those two different vectors together. Okay, now the way we do this is that if you take vector A and then you multiply by vector B through the dot product, and you'll notice here that the way we show this is you draw a little tiny dot indicating that it is a dot product between the two different vectors, A dot B. Now that would be equal to take the two x components, multiply them together, add that to the two y components, multiply them together, and add that to the two z components, multiply them together. Therefore, vector A dotted with B, vector B, would be equal to ax bx plus ay by plus az bz. Or, another way you can calculate it, and this way is actually significantly easier if you actually have the information to do it, is if you take vector A and you dot it with vector B, that is equal to the magnitude of vector A times the magnitude of vector B multiplied by cosine of theta. In this equation, cosine of theta would represent the smallest angle between vector A and vector B. Now, it turns out you can actually use that equation to get the equation that we're familiar with, work from Physics 20. So let's say that we had a force vector F, and then you dotted it with a displacement vector D. This would be equivalent to the magnitude of the force vector times the magnitude of the displacement vector times cosine of theta, and that's actually equal to work. And if you go back to the Physics 20 formula sheet, that's the equation of work that is being presented. Okay, so the reason that it's work is the magnitude of the force times the displacement, magnitude of the displacement times cosine of theta, is because work is actually a vector dot product between force and displacement. Okay, so let's do an example. So we have a constant applied force, which is represented by a vector. This is in three-dimensional space. Okay, we don't need to worry about what this looks like as much as just like dealing with the actual vector math. Okay, so it's represented by the force vector, 10, 18, negative 6 newtons. And this force vector changes the position of my object along a straight line. It says if the displacement of the object is represented by the vector d, 2, 6, 15 meters, calculate the work done by the applied force on the object and calculate the angle between the force and the displacement vectors. Okay, so by applying this force up here, what we're doing is we're causing the object to change position, where it would move positive 2 meters in the x direction, and then it would move positive 6 meters in the y direction, positive 15 meters in the z direction. And then if you just drew a vector from like the start to the finish, that just represent the actual displacement of the object. Okay, so let's go ahead and calculate this. Okay, so I want to calculate the work done by the applied force. So I know work is equal to, it's the vector dot product between my force vector and my displacement vector. Okay, that's the equation I have to use to calculate work because I don't know what theta is. So I couldn't use this boxed purple equation here to do it because I don't know what the angle between the force vector and the displacement vector is. Not yet anyways. Okay, so we're gonna have to use the top equation here to do this. So what this would then look like is this would be equal to the x component of the force times the x component of the displacement plus the y component of the force times the y component of the displacement plus the z component of the force times the z component of the displacement. Okay, now we can just plug numbers in and calculate this. So this would be equal to the x component is of the force vector is 10 newtons. The x component of the displacement vector is 2 meters. Plus the y component of the force vector is 18 newtons. The y component of the displacement vector is 6 meters. Plus the z component of the force vector is negative 6 newtons. Multiplied by the z component of the displacement vector, which is 15 meters. Okay, let's just double check to see we did that correctly. So we're going to go 10 times 2 plus 18 times 6 plus negative 6 times 15. Okay, so if we calculate this correctly, so we're actually just going to get a single numerical value then. So the single numerical value would be a positive number, and it would be positive 38 joules. Okay, so what I did here is I took two vectors, force and displacement, as ordered triples. I completed the dot product, which actually just gave me a single scalar quantity then. That scalar quantity is positive 38 joules. Positive work just means you're putting energy into the object. Okay, now B says figure out what the angle is between the force and displacement vector. Well, we can actually use our other equation to do this. So our other equation would tell us that work, so we go back here, so we can now use this equation to figure out what the angle is. Because we know we can also write down the vector dot product as the magnitude of the two vectors times cosine of theta. Okay, so I know that work is F times D. But another way to calculate that would be magnitude of the force vector times the displacement vector times cosine of theta. And what I want to do here is I just want to, I want to get cosine of theta isolated. Okay, so if I isolate cosine of theta, I would then have cosine of theta would be equal to, so we're just gonna look at work equals FD cos theta, so that'd be W divided by F times D. Now, I can't complete this calculation yet because I don't know what the magnitude of the force is and I don't know what the magnitude of the displacement is, but we can calculate those. Okay, so the magnitude of a three-dimensional vector is just you're going to take the sum of all the squares and then take the square root. So this would be the magnitude of the force vector would be 10 newtons. all squared plus 18 newtons all squared plus -6 newtons all squared. And then we're going to take the square root of that number. Okay, so that would give me my force would then be equal to, let's go to the nearest tenth of a decimal, so this would be 21.4 newtons. Okay, so now I know F. But I also need to know the magnitude of the displacement vector, which is D. So again, take the sum of the squares. So that would be 2 meters, all squared, plus 6 meters, all squared, plus 15 meters, all squared. Take the square root of this. Again, this is the magnitude of a three-dimensional vector. And then I would get my displacement would be equal to, again, to the nearest tenth of a decimal, it'd be 16.3 meters. Okay, now I want to calculate what the value of theta is. And I can do this, I now know what the work is. It's positive 38 joules. I know what the magnitude of force is. I know what the magnitude of the displacement is. So I just plug numbers into the equation now. So I'd have theta would be equal to the inverse cosine of W, which is positive 38 joules, divided by the force, which is 21.4 newtons, multiplied by 16.3 meters. And then as long as we make sure our calculator is in degrees mode, we should get an angle that is 84 degrees. Okay, so that's what theta represents in the dot product. Theta represents the smallest angle between the two vectors that you are dotting together. Okay, that's a dot product. Dot product, not too bad, okay? Now let's get into the cross product, which is a tedious nightmare, okay, compared to like what a dot product is. Okay, so the vector cross product involves taking two vectors, multiplying them together, and this time it gives you a vector, okay? So this should be the immediate indication that this is tougher, okay? As soon as you're dealing with vectors in comparison to scalars, vectors are always more complicated to deal with because you have to worry about so many different components. So as per like the dot product was multiplication of two vectors to get a single number of scalar, cross product is going to be two vectors that give you another three-dimensional vector. So again, that is going to be a bit of a pain to actually deal with. Now, an example of this is in Physics 20 AP. We talk a little bit about torque. And actually, we talked about torque a bit in the magnetic forces and fields unit. We were talking about like the magnetic deflecting force acting on the armature of like an electric motor. All torque is torque is a force that causes rotation. Okay, so my equation for torque is it's equal to R, which represents the lever arm from a pivot point, times the force that's acting on it. So if I want to draw a quick picture here, like let's say I had like a little pivot point and there's like a beam attached to it. And then I'll say I'm applying a force maybe like this. So apply a force in like this direction. Okay, so your lever arm, which is R, that's just a vector that starts at the pivot point and goes to where your force is. So if I want to draw the R vector here, the R vector would just be this, okay? So that's what we call the lever arm. Okay, now let's look at this more from like generic mathematical variables. So let's again introduce those two three-dimensional vectors. So I have vector A, which has components AX, AY, AZ. And I have vector B, which incorporates components BX, BY, and BZ. And then I want to figure out what the cross product is equal to. And let's see what it is. Ugh. Yeah, already you can see it's a little more complicated. So what I have is A cross B. Now this gives you another vector. So what it's going to give you is it's going to give you another ordered triple, which means you're going to have three values in the ordered triple. Now, what this is equal to is the first value of the ordered triple would be equal to, if you take AY, multiply by BZ, and subtract AZ times BY, that evaluated expression would give you the first value in the ordered triple. Okay, so that's going to be value number 1. Okay, and then if you take AZ, multiply by BX, subtract AX, multiply by BZ, that would give you the second value in the ordered triple. And then if you take AX, multiply by BY, and then subtract AY times BX, you would get the third point in the ordered triple, or the third value in the ordered triple. Okay, so again, tougher than a dot product because you're actually getting 3 different values, and then each of those values involve evaluating an expression. Okay, now oftentimes when we're evaluating a vector cross product, we're only interested in what the magnitude of the vector is. We're not really interested in the direction. And it turns out if you're just going to calculate the magnitude of a cross product, it's actually a lot easier to do. So let's just say I didn't want to worry about the direction of a vector cross product. All I want to know was what the magnitude of the vector would be. So the magnitude of that vector would be, so let's say we wanted the magnitude of A cross B. That would be equal to the magnitude of A times the magnitude of B times sine theta. Okay, so it looks pretty similar to like the dot product equation, except we have sine instead of cosine. But this only tells you the magnitude of the vector. It does not tell you the direction. So again, we can use the torque as an example here. Okay, so we know that torque is a vector cross product between your lever arm and the force. Now let's say you wanted the magnitude of torque. So the magnitude of torque would then be equal to the magnitude of the lever arm times F. And then this would just then be equal to, your torque would be equal to the magnitude of R times the magnitude of F multiplied by sine of theta. Okay. And then once again, A just represents the smallest angle between A and B. So if we were to go back up to my picture here where I drew like my lever arm and my force vector, your angle theta would just be the smallest angle between those two vectors, which basically tells you how you can maximize torque. So if you want to maximize torque, you would need sine of theta to be equal to 1, which means you need a theta value of 90 degrees. So if you were actually to apply a force just vertically upward on the end of this beam here, that would generate the greatest amount of torque. If you had sine of 0, which means you'd apply a force directly in line with the actual beam, you wouldn't generate any torque at all. Again, that would be equivalent to like going up to a door and just like pushing on, trying to like open the door by like pushing on the end of it. Like nothing would happen. You don't generate any torque. Okay, so that is how you could calculate just the magnitude of like a vector cross product, again, which is not too bad, okay? However, often we need to know what the direction is as well. Now, to figure out the direction of a vector cross product, believe it or not, we've already done this, okay? We talked about, in the magnetic forces and fields unit, something called the third hand rule. What did we use the third hand rule to do? Well, we used it to predict if you have like a moving charge going through a magnetic field, it can tell you what direction is the deflecting force. Okay, and we're actually going to use as an example in a moment here. Okay, so here you have like a 3-dimensional grid. So if we look at this, we have a couple of vectors. So I have vector, let's go different color here. I have vector A and I have vector B. Okay, so back when we were doing these problems, like we would have given some more physical meaning to these two different vectors here. So we would have said, like, for example, if we have a charged particle going through a magnetic field, we would have used our thumb to represent the direction of the particle's velocity. We would have used our fingers to represent the direction of the magnetic field. And then it turns out the direction of the open palm, which is the magnetic deflecting force, is going to involve some kind of a vector cross product between these two guys. It's not just flat out V times B because we have the Q involved in there. But if we have our thumb representing one vector, we have our fingers representing another one, then the vector cross product of those two vectors would be represented by the direction open palm would face. I did want to point out, though, that this is valid only with the right hand when we talk about calculating a mathematical vector cross product. I know we did things like when we use the right hand to represent a positive charge and the left hand for a negative charge, but when we're talking about in the strict mathematical sense, we'll just use the right hand to deal with this. Okay, let's summarize this picture a little bit. Your thumb would point in the direction of vector A. And again, if you wanted like an actual physical vector in terms of physical meaning, that could be the direction a particle is moving in a magnetic field. Your fingers point in the direction of your second vector. So that would be the direction of the magnetic field. Again, if we have a charged particle going through a magnetic field. And then the cross product of vector A times vector B. So if I wanted to know what the direction of the cross product would be, it'd be the direction that my open palm would face if you use the right hand rule, the third hand rule with the right hand. So we can actually do this in two different parts. So what we could do is we could, if we wanted to figure out like what a vector cross product is, we could use equation 12 to figure out its magnitude. And we could use the third hand rule with the right hand to figure out what the direction is, okay? And then we can kind of put the two of them together. And I'll illustrate that now in an example in a moment. Okay, so I said because equation 11, so let's go back to equation 11. Equation 11 was like that bit of a nightmare equation where you had like all these different expressions to evaluate. So because that equation is tedious to evaluate, sometimes it's more practical just to figure out the magnitude and direction of a vector cross product separately. So we can figure out the magnitude of a vector cross product by using equation 12, which is the magnitude of a vector cross product as AB sine theta. And then we can get the direction by using the third hand rule. And then we can kind of put the two different techniques together to identify what direction the vector would actually point. Okay, let's try to make sense of this. So I've already been making reference to like a charged particle going through a magnetic field. So let's try to use this vector cross product knowledge to actually do this now. Okay, so it says an electron is moving at a constant velocity of, and again, I have vectors in three-dimensional notation, although it turns out right here that I believe the z coordinate is just 0 for all these vectors. So we don't have to worry about the z coordinate just right now. Okay, so it has a velocity of -2 times 10 to the 7. That's pretty fast. It's approaching like relativistic speeds. I don't know how realistic that is. 3 times 10 to the 7, 0. In a magnetic field of B, -20, 0 Teslas. And what I want to do is I want to calculate the magnitude of the magnetic deflecting force acting on the electron by basically calculating the magnitude and direction separately, and then writing as an ordered triple and in Cartesian vector notation. Okay, so there is a lot to do here. Okay, so I think what we're going to start off by doing is we're just going to try to calculate what is the magnitude of the magnetic deflecting force. Okay, now the actual equation, okay, so I'll write it here. The actual equation, if we write down the actual equation for the magnetic deflecting force, the magnetic deflecting force is equal to the charge, and then it's the cross product between the velocity of the particle and between the magnetic field. Okay, now that's not the equation we're familiar with on the Physics 30 formula sheet. So let me just show you how we can get the equation on the formula sheet. So the equation on the formula sheet for magnetic deflecting force tells me the magnitude of this force. So let's put absolute value signs around it. So we'd have absolute value, magnitude. Now, what I'm going to do on the right-hand side is I'm going to put a magnitude sign around the Q and a magnitude sign around the cross product separately. So I can write down the magnitude of the deflecting magnetic force is the magnitude of the charge multiplied by the magnitude of the vector cross product between V and B. Now, what we need to do is we need to expand what the magnitude of this vector cross product is. And here's what we know. We know that if you take two vectors, you cross them together, this would be the magnitude would be equal to the magnitude of A times the magnitude of B times sine of theta. Okay, so if I expand this correctly, this would then be the magnitude of the deflecting force would be equal to Q. And then, well, what's the magnitude of a vector cross product? You take the magnitude of the two vectors and multiply by sine theta. So this would actually turn into Q, V, B, sine theta. Because the magnitude of V cross B is VB sine theta. Now, that should look familiar because that's the equation we are using in Physics 30 to calculate the magnitude of the deflecting magnetic force. We just didn't know at the time that it was actually a vector cross product between V and B, okay? Because like we didn't want to introduce that math at that point because it's quite a bit more complicated. Okay, now to calculate the magnitude of the deflecting magnetic force, I need to know two things. I need to know what the magnitude of the velocity is. I need to know what the magnitude of the deflecting magnetic force is, the magnetic field is, and I also need to know what theta is. Okay, Q is not a problem, okay, because it's an electron. So the magnitude of charge would just be the magnitude of negative 1.60 times 10 to the negative 19 coulombs. Okay, so that would just be 1.60 times 10 to the negative 19 coulombs. Okay, so no problem with that. Now, V, again, we're going to figure out the magnitude of a three-dimensional vector, although this vector is not three-dimensional because it doesn't have a Z component. So just find the sum of the squares. So this would be negative 2 times 10 to the 7 meters per second, all squared, plus 3 times 10 to the 7 meters per second, all squared. And if you wanted to add the Z value, you could. It's just 0. And then we just take the square root of that. Okay, so that's going to give me V would then be equal to, and let's go to, I'm going to go to 3 significant digits. So I'll say it's 3.61 times 10 to the power of 7 meters per second. Okay, and then let's also calculate what the magnitude of B is. Well, that's easy. Okay, the magnitude of B would just be, well, it only has one component to it. So it would just be 20 Teslas. Now, if you wanted to show the work, you could go ahead and do it. So it would be like negative 20 Tesla squared plus 0 squared plus 0 squared, and then take the square root of that. And this would give you your magnetic field would just be equal to 20 Tesla. Okay, so to calculate the deflecting magnetic force, okay, because it says figure out the magnitude and direction separately, okay, we almost have every piece of the magnitude, okay, because what we have right now is we have the value of Q, okay, which is this value. We have the value of V, which is this value. we have the value of B, which is the 20 teslas. So the only thing we don't have is we don't have what the sine of theta is. Okay, now this is where it gets a bit more complicated because we need to draw a picture to try to figure out what theta is going to be. Okay, I'll do that on the next slide here. Okay, so what I'm going to do is I'm first of all going to draw a three-dimensional Cartesian plane. Okay, I'll just do it in blue here because I'm going to draw on top of it in a moment. Okay, so let's say I have a z-axis that points towards the top of the page. And I have an x-axis that points towards the right side of the page. And then we have a y-axis. Sorry, let's say the z-axis goes towards the top of the page. The x-axis goes towards the right side of the page. And my y-axis would go into and out of the page. So I'll draw the y-axis in this direction. Okay, we'll say that's the y-axis. Okay, so positive x-axis towards the right side of the page, positive z-axis towards the top of the page, and then the y-axis is going to be into the page. Okay, and if I want to, I can just extend it, so I can also show it coming out of the page a little bit right here. Okay, and I'll extend the x-axis a little bit over here as well. Okay, so make this guy go a little bit over to the side. Okay, now what I want to do is on this grid, we can do the z-axis too. I could just go down here. Is I want to go back here and I want to actually sketch the vector v, which is -2 times 10 to the 7, and then 3 times 10 to the 7 meters per second. Okay, I'm just going to rewrite this vector out here so we don't have to flip back to the other page. So, okay, so my velocity vector as an ordered triple was equal to, you have -2 times 10 to the 7. You have 3 times 10 to the 7. And you have no z component. Okay, I'm going to try to sketch this vector on the Cartesian plane. Okay, so what we have here is this first value is the x component of the vector. So we can call that vx. This is the y component of the vector, vy. And this is the z component of the vector, vz. Okay, now if I want to sketch this, so what I would do is from the origin, I'm first of all going to draw the x components. The x component goes in the negative x direction, so it would go somewhere in this direction here, okay? So it's going to point in this direction. Okay, so we'll call that vx. Now, adding vectors tip to tail, I then add the y component. Now, what the y component does is the y component is going to go in the positive y direction, which is actually into the page. So I'll draw into the page by drawing a line that's parallel to that y-axis here. Okay, so as best as I can, let's just draw it so it's parallel to the y-axis. We're going to call that vy. And then my resultant vector, so maybe let's pick a different color for this one. The resultant vector, I'll just do it in green, is a vector that's going to go from start to finish. Okay, so it would then point in this direction. So we'll call this, that's my actual resultant velocity. I don't know if this helps, but I can shade it in like this, maybe just to make it stand out. So this triangle actually only exists in the y-x plane of like the picture here. There's no part of this velocity diagram that's in the z direction at all. Okay, now the magnetic field, if we go back here, only has an x component. So the magnetic field is -20, 0, 0, and it has units of Teslas. Okay, so if we drew the magnetic field vector, and I'll do this in purple, would just be a vector that goes in the negative x direction. So it would also point in this direction here. Okay, B. And what I want to know is I want to know what is the angle between my velocity vector and between the and between the velocity vector and the magnetic field. So it's this angle theta that I want to calculate here. Okay, because everything's just occurring in like a y-x plane here, what I'm going to do is I'm just going to draw a picture of just the y-x axis just to make this picture a bit more clear. Okay, so let's view this from like a top view perspective. Okay, so let's say that we have, here's the y-axis, here's the x-axis. We're not going to worry about the z-axis because there's no part of the velocity or magnetic field vectors that point in that direction. Okay, so to redraw my picture, for my velocity vector, I have an x component that goes towards the left. I have, which we'll call vx. I have a y component that goes in the positive y direction, so vy. And then the actual velocity vector itself would just be from the origin to the tip of the vy vector. Okay, so that's the triangle I was trying to like shade in like on the picture here. Just hard to draw in 3 dimensions. Okay, now we also have the magnetic field vector, which points in this direction. So that's B. And what we want is the angle theta. Now, to calculate theta, we can actually just use the information about the y component and the x component to figure out theta. We have a right angle triangle where I know what vy is and I know what vx is. So I can use the tan ratio to figure out what the angle theta is. So what I could say here is I could say tan of theta is equal to side opposite, which is vy, divided by side adjacent, which is vx. Okay, so if we plug the numbers in, this would then be theta would be equal to the inverse tan of, okay, we're just doing magnitude here. So vy is 3 times 10 to the 7 meters per second, divide by 2 times 10 to the 7 meters per second. Then that's going to give me an angle theta that would be equal to, let's give like one decimal place here. So we'll say 56.3 degrees. Okay, now we have all the information we need to calculate the magnetic deflecting force. So your magnetic deflecting force, the magnitude, was equal to Q times V times B times sine theta. Okay, so let's plug numbers in and calculate it now. So Q, it's the magnitude of the charge of an electron, so that's 1.60 times 10 to the negative 19 coulombs. Multiply by the magnitude of the velocity, which we got on the previous slide. It was 3.61 times 10 to the 7. Multiply by the magnitude of the magnetic field strength, which is just 20 teslas. Multiply by sine of 56.3 degrees. Okay, this will give me the magnitude of the deflecting magnetic force, would then be equal to 9.6 times 10 to the negative 11 newtons. Now, we only have one part of the answer. It says calculate the magnetic deflecting force by determining the magnitude. Okay, so we've done that. But we also need to know what the direction is. Now, to get the direction, we're going to use the third-hand rule. Okay? So, direction. We're going to use third-hand rule. And we're going to use the left hand here because we're going to, we're dealing with an electron. So third hand rule with left hand. Okay, so that is because we're dealing with an electron. Okay, so quick review of the third hand rule from Physics 30. So your thumb points in the direction of the particle's velocity. So if you look here, that would be in the, now you gotta be careful. So if you look at this picture, which component of the particle's velocity is actually going to experience a deflecting force? So again, I'm gonna look at like our theta in the equation here. If a particle is moving in the same direction as the magnetic field, like if we were moving only in the Vx direction, it would not be subjected to a deflecting force. So it's only the perpendicular component that actually experiences a deflecting magnetic force. So therefore, we're looking at Vy because it's perpendicular to B. Okay, charged particles are only affected by a magnetic field if there's at least a component that's perpendicular to it. So in this case right here, it's that Vy component. So that Vy component, that points in the, if you look at the picture here, that Vy component points in the, I'll call it the positive Y direction. Oops. Okay, your fingers point in the direction of the magnetic field. Okay, what direction does the magnetic field point? It points in the negative X direction. Okay, and then your palm, which is the deflecting magnetic force. Okay, this is where you have to use the third hand rule now. Okay, so what I would do is take your left hand, make sure your thumb and fingers are perpendicular to each other. Now, if we look at the picture at the top here, okay, so sorry about that again. Okay, so if we take your thumb and you point it in the direction of the perpendicular component of the particle's velocity, that would actually point into the page, okay, because into the page would be the positive Y direction. You then take your fingers and you point them in the negative X direction. So the negative X direction would then be pointing towards the left side of the page. Okay, so with your left hand, your fingers are pointing towards the left, the direction of the magnetic field. That's a negative X direction. Your thumb points in the direction of the component of the particle's velocity perpendicular to the field. That's into the page in the positive Y direction. And what direction does your open palm face? Well, my open palm then faces towards the bottom of the page, okay? Okay, and what direction is the bottom of the page? We'll look at this Cartesian grid here. The bottom of the page would actually be the negative Z direction. Okay, now we're ready to write this as an ordered triple. Okay, so now we can put the direction and the magnitude together. So we could do here is we can then say Fm would be equal to, okay, so open the ordered triple up. Okay, so Fm, so just kind of highlight this here. The deflecting magnetic force only has a Z component. It points in the negative Z direction. Therefore, it has no X component. It has no Y component. And the Z component would just be this magnitude value, 9.6 times 10 to the negative 11, but in the negative Z direction. So we'd actually have to write it down as negative 9.6 times 10 to the negative 11. And then we write down the units on the outside. So order triple is 0, 0, negative 9.6 times 10 to the negative 11 newtons. Okay, now that is writing it in as an order triple. So what we did here, again, just kind of review, is we figured out the magnitude separately, and then we figured out the direction separately, and we just kind of combined the two things to write down the order triple. Now, it also wants it written as a Cartesian vector. So Cartesian vector writes this with like the special unit vectors. Okay, so this would be Fm, would then be equal to, okay, so this would be the x component times a special unit vector I, plus the y component times a special unit vector j, minus 9.6 times 10 to the negative 11 newtons. Oh, let's not write the units here yet. Let's get rid of that. Ten to the negative 11. Oh, gotta write in the special unit vector. Go away. It doesn't want to leave. Okay. Okay, let's write down k here. Oh, there it goes. Okay, and then squiggly brackets, and then newtons. However, if the x and y components are 0, anything multiplied by those unit vectors would just eliminate. Therefore, we could just write down in Cartesian vector notation the magnetic deflecting force, Fm, would just be equal to squiggly bracket, negative 9.6 times 10 to the negative 11. Sorry, I don't know why it keeps going to the next slide here. 10 to the negative 11. And then we have the special unit vector k. Close this off and write the units on the outside. So that would be my answer as a vector in the Cartesian vector notation. Okay, so this is one way we could have done this. Okay, so the way we evaluated the vector cross product, okay, so the way we evaluated this cross product, highlight it right here, is we figured out the magnitude first, then we figure out the direction using the third hand rule, and then we can combine them. But we can actually just do a flat out mathematical calculation to do this, which we'll kind of get into in a moment. Okay, so I said if the vector cross product needs to be evaluated, it's often easier to use something called determinant notation. Okay, so this is going to be another thing that would like be introduced to you like when you start to take like a linear algebra course in university. Okay, so let's look at what determinant notation would be. Okay, so a determinant of order 2 is defined by the following. Okay, this will seem like a little bit like out of nowhere at first. Okay, so what I have here is I have a couple of like vertical lines. And it's kind of like I have a table. So if you thought of like this as a table here, this would be a table that would have 2 rows and it would have 2 columns. So this would be like a 2 by 2 table. So we refer to that as a determinant of order 2 because it has 2 rows and it has 2 columns to it. Okay, now inside this this determinant here, this is essentially what these values mean. So if we have it written where we have like ax, ay in a row, and then bx, by in a row, and we write down these absolute value signs around it, that's telling me to calculate something called the determinant. Now, the way that a determinant works is it's just a way of telling us how to evaluate this thing. So the way to evaluate this determinant would be you take ax multiplied by by, and then subtract ay multiplied by bx. So what I'm actually multiplying here is I'm multiplying and multiplying the things that are across from each other. Now, if you wanted a really simple example of what this might look like, okay, let's say I actually put like real numerical values in here. So like, let's say that I had like 3, maybe like -4, maybe I have like a 5 here, maybe I have a -2 here, okay? And you want to evaluate that determinant. This would be equal to, okay, you take AX multiplied by BY, so that would be 3 multiply by -2, subtract, and then you go AY, which is -4, multiply by 5. Okay, so this would then be 3 times -2 is -6, and then you're going to subtract -20, add a negative, so this would then be equal to 14. Okay, so anytime you see like a couple of like components specifically, and they're arranged in like this kind of like table format where you have like rows and columns, if you have like the absolute value signs on the outside, this is telling you to calculate something called a determinant. Okay, and a determinant of order 2 is one where you have 2 rows, 2 columns. And the way to evaluate it is you go AX times BY, subtract AY times BX. Now, if only things were that simple. Well, what if you have a determinant of order 3? Oh, great. So determinant of order 3 would mean that you have a 3 by 3 kind of like table that we want to calculate the value of. What would this look like? Oh my goodness. So you know how I said that vector cross products can be kind of like tedious? Like we'll show this determinant is involved in a vector cross product in a moment, but it's like, what am I looking at here? Okay, well, let's try to break it down. Okay, so on the left-hand side, we have a table where in the top row of the table, I have AX, AY, AZ. In the bottom part of the table, I have BX, middle row, BX, BY, BZ. And in the bottom part, we have CX, CY, CZ. Now, it turns out if you want to actually figure out the determinant of like a kind of like a 3 by 3 type table, you can actually break it into a bunch of order 2 determinants. So the way we break it down, I'll show you a little trick to like memorize this a bit more in a second, is you'd figure out the determinant of BY, BZ, CY, CZ, multiply by AX. You would subtract the determinant of BX, BZ, CX, CZ times AY, and then you would add the determinant BX, BY, CX, CY multiplied by AZ, and that would actually evaluate this whole thing. Now, because it's so insanely tedious, I'm not going to show you an example just quite yet of how to do this. I'm going to show you a bit of a trick where we can actually kind of like simplify this a bit. But first of all, we need to see how this actually applies to like our vector cross product. Okay, so let's say we have 2 vectors, and these 2 vectors, instead of writing them as ordered triples, we're going to write them in Cartesian vector notation. So if A was written as an ordered triple, it would be AX, comma, AY, comma, AZ. B would be BX, comma, BY, comma, BZ. But in Cartesian vector notation, I have vector A as AX times I plus AY times J plus AZ times K. And vector B would be equal to BX times I plus BY times J plus BZ times K. Then, if I want to calculate the vector cross product of these 2 vectors, so again, this is where the whole like understanding of the determinant is going to come in. All we have to do is calculate the determinant of this. Okay, so what we would do here is to figure out the cross product of A times B. In the top row, we write down our 3 special unit vectors, okay? So we have I, J, K. In the second row, we write down vector A. In the third row, we write down vector B. Now the columns, you'll see how the columns match up with the individual components. The special unit vector I attaches to the x components of a vector. So in this column, you have I, ax, bx. Special unit vector j is attached to the y components. You have ay, by. And special unit vector k is attached to the z components. You'd have az, bz. Okay, now, if I wanted to calculate this, well, we'd have to like expand it in terms of like how you've written down a determinant here, okay? That's what the cross product of A times B would be. It's going to be the determinant of like this 3 by 3 grid we've kind of set up here. Okay, so then A cross B would then be, you would have AY times AZ, BY, I'm sorry, you'd have the determinant AY, AZ, BY, BZ times special unit vector I minus determinant of AX, AZ, BX, BZ times special unit vector J plus the determinant of AX, AY, BX, BY times special unit vector K. Okay, well, box set equation is another one that's going to be on the formula sheet. Or if you want to actually break the determinant down. So just remember, when you're figuring out a 2 by 2 determinant, it's going to be, you'll go this times this first, and then you're going to go subtract this times this second. So we could also write it down as this. We could say A cross B is, in brackets, AYBZ minus AZBY times special unit vector I, subtract, in brackets, AXBZ minus AZBX, close the bracket, multiplied by special unit vector J, plus AXBY minus AYBX, close the bracket, multiplied by special unit vector K. Now, I'm going to, like I said, I'm going to show you a trick in a second where you can actually like do this like pretty easily without even having to like do a whole lot of memorization. Okay. Now, what I'm going to do is we're going to use this to go back and solve that previous example with the magnetic deflecting force, okay? And this is actually going to be a lot easier, okay? Believe it or not, in comparison to the way we did it in the previous one where we figured out the magnitude and the direction separately. Okay, so this is the exact same example problem that we had before. Okay, so what we want to do is we want to calculate the magnetic deflecting force, and we want to do it by evaluating a vector cross product. Okay, so Fm, we know, is equal to Q, and then V crossed with B. Okay, so the vector cross product that I'm concerned about here is, I'm just worried about this part, okay? This is the part where we have to worry about the vector cross product for. Okay, so let's write this out in like a two-dimensional, or in an actual like grid, okay? So we're gonna write down the cross product of V and B. Okay, let's set up our 3 by 3 determinant. Okay, the top row of the 3 by 3 determinant would just be your special unit vectors. You'd have I, you'd have J, and you'd have K. The second row is going to represent the first vector. So this is going to be Vx, this is going to be Vy, and this is going to be Vz. And make sure your components match up with like the column the special unit vector is in. And then the third row is going to be the second vector. So that's going to be vector B. So you'd have Bx, you'd have By, and you'd have Bz. Okay, but let's replace this with actual numerical values, okay? So I'm actually gonna give myself a bit more space to do this. So let's go to this page here. Okay, so let's do V crossed with B would be equal to the 3 by 3 determinant of, you have I, J, K, and then let's plug the numbers in. Okay, so Actually, I need to give myself more space here. Actually, no, there's no z component. Okay, so the x component of the velocity vector is -2 times 10 to the power of 7. The x component of the y component of the velocity vector is 3 times 10 to the 7. There is no z component for that vector. And then the third row, the x component of the magnetic field is 0. The y component of the magnetic field is 0. And the z component of the magnetic field, oh, sorry, other way around. There's no z component, sorry. I'm thinking of the magnetic force, so let's just fix that. The x component of the magnetic field is -20. Okay, so what we need to do now is we need to evaluate this 3×3 determinant, and that's going to actually tell us what the vector cross product v crossed with b is. Now, we could do it by basically just plugging numbers into equation number 15. There's no problem at all. You can do that. Now, when I was taught this in first year of engineering, in terms of like a trick that you could actually use to like memorize this pretty easily, here's how we do this. Okay, so I'll show you the trick. Now, if you don't like the trick, you can simply just use the mathematical formula, no big deal. But here's the trick that you can use. Okay, so the first thing I'm going to do is I'm going to try to figure out what value is being multiplied by I. Okay, so we're going to start off by figuring out what's going to be the x coordinate of this vector cross product. Now, the way it was explained to me is if we're going to start off by figuring out what I is, okay, so let's do this. So we're going to figure out what I is. What you do is whatever row or column I is in, just cross that row out. So I'm going to take a line, I'm going to cross this column out, and I'm going to cross this row out. Okay. Now, what's left here is what we're going to figure out a 2×2 determinant of. So what's left here now is this. Okay. So we're going to take the special unit vector I and we're going to multiply by the 2×2 determinant that remains. Okay, so what does that 2×2 determinant look like? Okay, so that would be I multiplied by, again, 2×2 determinant's not hard to memorize. It's kind of like multiply by the cross, go across. So this would be 3 times 10 to the 7. And you know what, let's just not write the units right now because it's going to get just a little bit irritating to write. So this would be 3 times 10 to the 7 times 0. And then we subtract, we go the other way across. So that would be 0 times 0. Well, guess what? This is all equal to 0. So this entire thing is just going to turn into 0. Okay? So actually, there is going to be no, there's going to be no x component of this vector cross product. Okay, now we then need to deal with the what's the y coordinate? Okay, the j part. Now, the one thing you have to watch out for here is this is not like an error. When you're actually figuring out the j component, we subtract, okay? So there must be a subtraction sign that's going to be in front of it. So here, I'm going to put a subtraction sign, and here's how I would evaluate this one. Okay, so first of all, let's get rid of these lines here. Okay, so get rid of that, get rid of that, get rid of this. Okay, so what am I trying to figure out here? I want to figure out what the y component is, so the special unit vector j. Now again, what I'm going to do is I'm going to cross off any values that are in the same row or columns as j. Okay, so I'm going to cross this out here, cross out the row that j is in, and cross out the column that j is in. Now, whatever remains is going to tell you what to figure out the determinant of. So my remaining determinant is going to be of this side and this side right here. So what I'm going to do to like calculate this is I'm going to go negative 2 times 10 to the 7 times 0, so go across that way. So let's put this in brackets. So this would be negative 2 times 10 to the 7. Okay, this times it's a 2 by 2 determinant. If you just ignore this middle row here, times 0. And then we subtract, go 0 times negative 20. Okay, you go across the other way. So 0 times negative 20, close it off. Well, once again, that just simply crosses off here, okay? Because that would all be equal to 0. And then we have the k component, the k part, the z component, okay? Now that is a plus. We go back here, okay? So it's positive plus for I, negative for j, and it's going to be positive for k. Okay, so the way I would do this now, again, if you like this trick, use it. If you don't use it. But this is, again, this is the way that like I was taught it in engineering that helped me memorize it. Okay, so what are we doing now? We're trying to figure out the z component, which involves a special unit vector k. So what I'm going to do now is cross out the row that k is in and cross out the column that k is in. And then all we have to do is figure out the determinant of what's left over. So the determinant of what's left over is just going to be this 2 by 2 grid that's left now. Okay, so then this would be negative 2 times 10 to the 7, multiply by 0, subtract 3 times 10 to the negative 7, multiply by negative 20. Okay, this part goes away because it's multiplication by 0. So the only thing we're going to be left with here is we're just going to be left with whatever the product of this is going to be. So therefore, we'd have V crossed with B. So V cross B would then be equal to, now it's up to you. We can write this in Cartesian vector notation. So I could go ahead and do that. What this would look like is it would then be negative 3 times 10 to the negative 7 times negative 20. Negative times a negative would be a positive. So that would actually give me 6 times 10 to the, times 10 to the 8. Six times 10 to the 8, multiplied by the special unit vector k, and then the units for this would just be meters per second times Teslas. Now, if you wanted to, we could also write it as an ordered triple. Okay, so as an ordered triple, it would look like V cross B would then be equal to 0, no x component, no y component, but I do have a z component. So the z component would be 6 times 10 to the 8. Okay, and then the units would be meters per second times Tesla. Now, the question doesn't want me just to calculate V cross B, it wants me to calculate the magnetic deflecting force. The magnetic deflecting force is Fm is equal to Q multiplied by the cross product of V cross B. Okay, this would be equal to, okay, what's the value of Q? Okay, now notice right here, we're not figuring out the absolute value of Q. So this would actually be the full charge of an electron. So that would be negative 1.60 times 10 to the negative 19 coulombs. And then we're going to multiply this by that vector cross product we just figured out. Okay, so we figure out that vector cross product of V cross B. So we're going to multiply by that ordered triple I just identified. So that ordered triple is 0, 0, 6 times 10 to the 8 meters per second times Tesla. Now, this guy right here is a scalar. So what we're doing just to finish this off is we're multiplying a scalar times a vector. So if you take a scalar constant and you multiply by a vector, all you do is you take the scalar and you just multiply it by the x component, the y component, and then the z component. So this would then give me the magnetic deflecting force as an ordered triple would then be, well, the first two you're multiplying by 0, so it'd be 0, comma 0, and then negative 1.6 10 to the negative 19 times 6 times 10 to the 8 would give you negative 9.6 times 10 to the negative 11, and the units would be newtons. If you multiply coulombs by meters per second times Tesla, it would give you newtons. Okay, that's what it would be as an ordered triple. And then as Cartesian vector notation, it would just look like negative 9.6 times 10 to the negative 11, times 10 to the negative 11, times the special unit vector k, and the units would be newtons. Now you notice here, this is the exact same answer as I got from example 3 using the other method. So this method involved figuring out the magnitude and direction separately and then combining them together. Okay. This method over here involved actually evaluating a vector cross product. Now it's up to you to decide, well, which method was less work? Was it this method? I mean, this method kind of looks like it's less work, but you need to understand how to evaluate a 3x3 determinant. And if you can do that using my trick and you can do it quickly, it's actually not that bad. Okay, this method involved less vector math. Okay, most of it was actually just stuff we did in physics 30, but it involved more steps because we had to use the hand rule separately to figure out the direction, as opposed to in this example, the math actually got the direction for me. I didn't have to use the hand rule at all to figure out the direction. The math got me the direction and it got me the magnitude all in one shot. Now, I suspect you're probably feeling extremely overwhelmed right now. This lesson was like super long, and the vector cross product, as you can see, like look at the page here, it looks like a disaster. Now, I can give you a little bit of reassurance. It turns out that most of the time in AP Physics, we only need to evaluate dot products, and if we have to evaluate cross products, we usually only have to figure out the magnitude. And figuring out the magnitude of a vector cross product is actually not that bad. So most of the stuff I kind of showed you today just gives you like an introduction to like what a dot product and a cross product are like. But it's like very unlikely we're going to have to actually evaluate a determinant at like any point in the actual AP Physics C curriculum. We'll find ways to get around it. But I did want to give like a full proper explanation as to how you do evaluate a vector cross product, even though we're probably not going to need to do this work most of the time. Okay, so you can practice this by completing the D2L quiz on vector multiplication. And then in the next lesson, we'll actually do an introduction to some very basic calculus. Although maybe I shouldn't say very basic because it might be kind of tricky to start off with, but we're not going to go too far in it in the next lesson. And I'll talk to you then.